Okay, thank you. And thank you to the organizers for inviting me and for organizing this such wonderful conference. So I'm going to talk about joint work with Gábor Lugosi, which is here. And so in this work, we wanted to understand the conversions of the classical stochastic gradient descent algorithm with in mind applications to deep neural networks. Okay, so let me start with the notation and the problem. So this is a very classical problem, classical minimization problem. Well, L is a loss function that can be either 0 or positive, okay? And the loss function has two parameters. One is the parameter to be learned, and that is the observation. So here I use two different dimensions, big D and small d. So we are going to work on the assumption that L is C2, and the observation is going to be a random vector taking values in RD. And this is the classical minimization problem of machine learning, that we want to minimize the population expected loss given a random variable Z. Okay, so the example that we know everything about is the linear regression example with square loss function. And here the parameter is just W transpose X. Okay, so let me write this here just to remember the problem. Okay, so sorry, W in RD. Right, so the first observation, so there is a large literature that tries to solve this problem. And the first observation is that here we are using the population expected loss instead of the empirical, which a lot of works are devoted to the empirical. And at some point, this makes a big difference for us. Okay, so population. Okay. Okay, so the classical way to solve this problem is to use stochastic gradient descent. Okay, and before that, so let me tell you the example we have in mind. So the idea is to solve the problem in general, but the example that we're going to treat later is the multi-layer feed-forward neural network that has appeared in in several talks. So maybe the notation is not exactly the same, but this is exactly the neural network that has been introduced in several of the talks this week. Okay, so we are going to take the square laws, and instead of the linear regression, we put a general nonlinear neural network that I denote by beta, omega x. So omega is going to be the parameter. Remember that it's in R big D, okay? And how is it defined, the beta? So there are the weights, which are matrices with several dimensions. These are the output layers. And sorry, W1 is the output layer, and the others are called the hidden layers. L is the depth that is going to be fixed for me. And the maximum of the dimensions is the width. Okay, these bias vectors are denoted by B. Okay, and the activation function, since I'm used to use the sigma later for my diffusion coefficient, I call it V. Okay, so the activated functions are called V. Okay, and then the parameter of the vector of the network is a vector that lies in RD, where D is given by this dimension, and it has both the matrices and the bias vectors. Okay, so this is going to be my notation, and this is once you have a W and an X, then these compositions of functions, as we have seen, this defines what we call neural network. Okay, so this is going to be the example that we have in mind. But the idea is to treat this problem generally. Okay, so we consider a stochastic gradient descent. Okay, so one has access to training data, which are going to be IID copies of Z. And then we consider stochastic gradient descent, which is that you start with an initial value, which is going to be non-random for us, and a step size eta. And then this is the classical stochastic gradient descent, which are iterate, you choose an IID copy of Z. Okay, And the gradient is always going to be, I don't put, just to simplify the notation, I just write gradient, but it's always the gradient with respect to W, of course. Okay, so this is a stochastic gradient descent. So the notation is eta gradient of L WK ZK, right? But instead of working directly with this algorithm, we, so following the fact that we were inspired by a result on deterministic gradient descent, which we first wrote the gradient descent as this. Right? So if you add and subtract the gradient of f, then you get gradient of L WK ZK. Right? So this is nothing, just adding and subtracting gradient of fk. And then here we recognize the usual deterministic gradient descent. Okay? And this term can be seen as a noise term that you put in the gradient descent. Okay? So there are a lot of works that are devoted to study this other process. But if you want to see this as a noise that you put and you want to get a limit that converges to, for example, a Gaussian noise, okay, then this is not the right scaling to use. Okay, so this is well explained in a paper by Peter Bartlett and Cheng, Yin, and Jordan. In 2020, okay, which says that, well, if this is not the right scaling to use if you want to take limits when eta goes to 0, right? So instead, what you need to do is to write this as square root of eta instead of eta, okay? And you can keep the other square root of eta to be the, so let's call it this one eta prime, and let's keep this as eta. Okay, so you split somehow you split the eta into square root of eta, and you call it, and you make the use differently. So this now eta prime is now the step size, and the eta is the let's say the variance of the noise. Right, and you call this psi of WKZK. This is the noise term. Okay. Okay, so this is well, they motivated very much this and in this paper, and they do simulations of this process. Okay, and also, so what you get finally, well, I just let me use an abuse of notation and write eta prime equal to eta, and then you get this process. Right? So this is not exactly gradient descent, it's an approximation of gradient descent, just using this different scaling for the noise term, right? Why is it useful? Because if you let eta go to 0, okay, using the writing eta as a step size, you get this continuous time process. Okay, now this square root of eta is this other square root of eta that remain there. Okay, so here the square root of eta remains fixed, and you let eta prime go to 0. Okay, so this converges to this process WT. So this process here. Okay, well, here I write it in integral form, so plus the square root of eta. Where B is a Brownian motion in RD. Remember that D is the dimension of the random variable. Oh, sorry, D is the dimension of the parameter space. Eta is fixed and acts as the variance of the noise, okay? And sigma is a D times D matrix defined as the unique square root of the covariance matrix of the gradient of the loss function, okay? So the conversions of this process to this one is very well understood. I mean, in this paper, they look at the Weierstrass distance between the densities of both processes and obtain conversions and convergence rates. And there is a lot of literature that shows these conversions. Let me just tell you about the heuristics of these conversions, which is not relevant for our work, but just to understand where this comes from and why do we need to scale the noise in a different way than just using the eta. Okay, so the idea is the following. So heuristics of the convergence. Okay, so the idea, so we are at T, okay, and we want to see this process as a discretization of this, right? The usual way to discretize an SDE is to use the Euler scheme, right? But the Euler scheme is not exactly equal to this because we have these ZK IID random variables here. Okay, so somehow we want to use the fact that ZK IID, and then when you discretize the sum of these variables will converge to the Gaussian distribution. Okay, so the idea is to first consider a step size of order of length t divided by n, okay? And then again, divide every interval of t divided by n by t divided by n squared. Okay? Now, so this is explained here. Sorry. Okay? So this is the first step. So this is here. Okay? What happens in this step is that right. So what happens from one step to the other is that you can just iterate, okay, the process from here to here. You just write it as the sum of the steps, okay? And then, so here, well, maybe instead of eta, I'm using delta in the slide. Sorry about that. So this is delta, just to, okay, I put eta prime, but then I'm using delta, so sorry, it's a bit messy, but so let's keep delta to be t divided by n, okay, the step size, and then let's iterate, okay? And then what we do is that we do this approximation of the gradient of FWTK, we approximate it, so here, for each smaller step, we approximate by the initial value, but only here, right? So for all these points here, WFFK and psi of WTK is approximated by W0ZK and by gradient of FW0, and you get this approximation. So this is done in the little step, okay? And then for here, we obtain the sum of IID. These allow us to take here the sum of IID random variables, which converges to a Gaussian band, the central limit theorem, okay? And then we get at time t divided by n, so we are here, this discrete process that is exactly the first step of the Euler-Murayama discretization, right? And then you do the same at the next step. You divide into little steps of size t divided by n squared, and again, you keep doing this process. Just adding here each steps just approximated by the value here so that you can use central limit theory in each of these little steps. And then each step corresponds to the Euler-Moyama discretization. Okay, so this was just for those that don't know where this continuous time SDE, this is just, but this is not relevant for our work, okay? Because in terms of conversions, either you study one, either you study the other, okay? Okay, so this is how do you obtain this process? Okay, so please remember, it's not exactly gradient descent, it's an approximation of gradient descent using this different scaling. Okay, and now keeping this eta as being just the amount of variance of the noise that you put, the amount of noise that you put. Okay, so now there is no more step size because we are now in continuous time. Okay, so you can see this as an approximation of the stochastic gradient descent algorithm, and this is the object that we started with. And now the question is, under which conditions on F and sigma, please remember sigma is the covariance matrix of the I mean, is the unique solution of the square of the covariance of the gradient of L, okay? So it's a fully nonlinear process in W, okay? And F is just the expectation of the loss function. Okay, so this is a fully nonlinear SDE, right? So most of the works that study convergence also, we realize that they use the typical Langevin SDE, where sigma is a constant, right? But here, if you want to be fully consistent with the general theory, sigma is fully nonlinear, and this makes the problem much difficult, okay? Right, so this is the object. And we were inspired by a paper by Chatterjee of 22, where he treats the case eta equal to 0, right? So gradient descent. And then Chatterjee, so let me keep this. So what Chatterjee does is to study the convergence of deterministic gradient descent, so eta equal to 0, to a global minimum of F under really mild conditions. Okay, which are the mild conditions? So this mild condition is, of course, beyond convexity, because when F is convex, everything is well known. Okay, and when F is not convex, there are works that assume this Polyak-Lojasiewicz condition. Okay, but most of the work assume this condition globally, right? And the problem is that this is for remember that we have neural networks in mind to apply, and this condition globally is not satisfied. Okay, so Chatterjee managed to get a result on convergence with a local Polyak-Lojasiewicz conditions. Okay, so what Chatterjee does is that he assumes that the minimum over W in a ball, in the closed ball of radius R and center W0 in RD, okay, where F doesn't vanish, of the gradient of F squared divided by F is lower bounded by 4 times F of W0 divided by R squared. Okay, so if you take an initial condition of the gradient descent W0 and an R that satisfy this condition, this being positive, okay? So you start with a point that is not a minimum, of course, otherwise, okay? And you take W0 and R satisfying this condition, then he shows that the gradient descent will converge in this ball. Okay, so this is really this Polyak-Lojasiewicz that I will call PL condition. It's a local PL condition, and really is among all the works because there is a large literature that study the convergence of gradient descent. This is really the minimum, a very weak condition. And then he shows how this condition is satisfied for neural networks, but with using the empirical expectation instead of the population as. Okay, so we were motivated by his by this work. Okay, and the idea is to extend his result and says what happens if we add to gradient descent this term and then it becomes a stochastic gradient descent. What can we say? Can we give sufficient conditions of this type on F and sigma such that we have convergence? Okay, so here, okay, so this is the main goal, right? And of course, the presence of noise introduces new challenges. Okay, so this is our goal. Right, so the first thing is that so maybe I should go back to the SDE. As I think it was mentioned also in a talk of the first day that he came up with an object, and in this case, it was a PDE, right? And he said, well, the first question that you need to ask when you get an equation is existence and uniqueness, right? So here, the thing is that most of the works that uses this PL condition and try to find a convergence result, they work on the assumption that F is Lipschitz. Okay, which is the natural assumption to get existence and uniqueness. But the problem is that when you replace L by our example of neural networks, this is not a Lipschitz function. Okay, so this was the first thing that we realized, that assuming F Lipschitz was too strong for our example. Okay, so and if you assume that the coefficient is not necessarily Lipschitz, then how do you prove existence and uniqueness? Okay, so the first thing that we did is to realize that the only thing that we could assume on the coefficients is a locally Lipschitz continuity. Okay, so that's what we assume. And under these, you cannot ensure existence and uniqueness. Okay, so all that you can ensure is the existence of a maximal local solution up to its blowout time. Right? So there is a probability that the solution blows up. Okay, and then there is no solution anymore, and then there is no stochastic gradient anymore. Okay, so this was the first challenging, really. Right, so the first problem was to assume only local Lipschitz conditions. Right, if you simulate this SDE with something that is not globally Lipschitz, the solution may explode. Right, now the question is, here we have minus the gradient that pushes you to the minimum, right? So the question is, can we ensure that the solution will not blow up if you start sufficiently close to the minimum? Well, with a certain probability, we managed to prove it, okay, but we don't have an almost sure result because it's difficult to prove that that the pushing of the equation to the minimum will beat the fact that the equation may explode. Okay, if you look at the trajectories of this process and you compare them with the trajectories of the deterministic process in a finite time, in a compact time, okay, you can show that when eta goes to 0, the trajectories will match, but not when t goes to infinity. Okay, or at least so far we still don't know. Okay, okay, so we can only consider this process up to its blowout time, that it's going to be called big T. Okay, and at this time the process blows up. Okay, so the algorithm doesn't converge. So this is the first assumption, and the second assumption is also important, and this is why for the applications this is quite restrictive, but this is the case to start with. Okay, so that the minimum is attained, and the value of f at the minimum is 0. Okay, so this ensures that if the process converges, we converge to a unique point. Right? So this ensures, which is equivalent to the interpolation assumption, that there exists omega so that L is 0 almost surely. So this ensures that at the minimum, the noise vanishes. So we converge to a point. If you don't put this assumption that the convergence is not to a single point, it will be around the minimum. And then it's a convergence in distribution to an invariant measure, right? And the problem is different. Okay, so here we were, I mean, it's more general, but, and it's typically the case in practice, but already showing conversions to a point, assuming that the existence of a global minimum was challenging enough to start with this first step. Okay, so this implies that the set of global minima, which is in practice infinity, so there are a lot of global minima, we just show the conversions to one global minimum. And the assumption is that there is at least one global minimum. Okay. No. I said that there exists one global minima. Exists at least one. No, in the most of the examples, the set of global minima is infinity.
Why is not sufficient here this condition with the gradient? Isn't the noise proportional to the gradient? You want the noise to vanish when you reach the minimum, but this is not about, isn't that about gradient?
No. You want also, well, yeah, you want also that the minimal value is 0. This is because otherwise, so this was an important assumption to ensure that the minimum value is 0, because if it's not, well, I don't remember if it.
The noise proportional to the gradient.
No, but he says y is 0 and not another value, right? That's what you're saying, or?
No, noise proportional to the gradient of F, if I remember correctly.
Yes.
So, I mean, if you want the noise to vanish, you need the gradient of L to vanish.
Which is good, but you.
That y equals x.
No, we really need this. It's not sufficient that the gradient is 0 for to get the minimum. Yes, but we also need the minimum 0 just to write the problem as that the loss function is 0, because then exactly y is going to be a function of x. Otherwise, it didn't work, actually. It didn't work, the approach. Okay, so, well, maybe I wanted to, right. So now I wanted to explain the method of the proof. Or maybe I should, okay, maybe I should give the theorem first, but it's just that I didn't, okay, sorry, okay. So, right. So how do the method of proof works? So we want to imitate a bit this Chatterjee, just looking into a ball, okay? And we want to show that if we start in this ball, okay? So if we consider the ball centered at the initial point, right? Then the process will converge in the ball with positive probability, okay? So we consider 2 stopping times. The first is the first exit time of the ball. And the second is, if in finite time we attain 0, then we're done, because 0 is the minimum, right? So we are only concerned on attaining the minimum at infinity, right? So we stop the process either when we exit the ball, either when we reach the minimum in finite time, right? And we consider this event, the event exiting the process and not having reached 0 at finite time. And we look at the probability at this event. And we were able to bound this probability by this quantity that I'm going to explain in a minute, and show that if this quantity is less than 1, I mean that this quantity quantifies this probability. So this is the probability that we don't exit the ball and we don't reach the minimum in finite time. Okay, and then condition on this event, then we have that the process converges almost sure to some point inside the set of minima, and the rate of convergence is exponential. Okay, so this is our result. Okay, So all the goal was to bound, this probability. And what is important is that when eta is 0, we get exactly the same condition as Chatterjee. Okay, so here this square root of f divided by r is exactly this guy. This A minimum is exactly this guy. Okay, so here we have this G max and beta and theta that appear because of the noise term. Okay, so this is the idea. Right, so what we observe is that when eta, we expected that when eta converges to 0, this probability converges to 0 as well. Right? Well, this is not true, and this is a method, the method of proof that didn't allow us to prove more. So this remains an open question to show that this probability converges to 0 when eta converges to 0. Okay. But our method of proof only allowed to show this, but it's already something, right? So this probability depends on R, on how far do you start from the real minimum or from one of the global minimum, how big is or small is your ball, okay? And how big or small is your eta, is the variance of the noise, so it depends. So for neural networks, we managed to prove that this probability can be as small as we want, okay? Right, and so now a word about the method of proof. The method of proof is really inspired once from the techniques by Chatterjee, but his techniques are deterministic, so merged with the theory of stochastic differential equations and Ito calculus. So when you have stochastic differential equations, there is the typical object that gives you stability is the Lyapunov exponent, okay, or a Lyapunov function. And this is exactly the log of fwt divided by t sup over t, okay, or the lim sup, let's say, lim sup when t goes to infinity, right? So you typically study this object. This is called the Lyapunov function, where v is a Lyapunov, so this is the Lyapunov exponent when f is a Lyapunov function, right? So here the key is to use, the problem is that, again, all these stability theorems for stochastic differential equations only work when the coefficients are Lipschitz, which they are, right? So we need to work with these stopping times, okay? We couldn't apply directly any stability result because our coefficients are not Lipschitz. Okay, so, but we could imitate the ideas, and the idea is to find a Lyapunov function that it's, and here the right Lyapunov function is the function f itself, right? And how do we prove this type of results? How do we prove that? So in order to prove how this limit is, which we expect to be 0, what we do is to apply Ito's formula. We apply Ito's formula to the log of fwt. Wt is an SDE, so there's Ito's formula in multidimensional in this case. And when you apply Ito's formula, you get A. A is exactly the object, this Polya-Ložović condition, gradient of f squared divided by f. But then there are two other objects that appear, which are the trace of sigma transpose sigma divided by f, and the trace of sigma transpose Asian of f sigma divided by 2f, okay? So here we also need to control the maximum of these two coefficients, okay? But as Eric was saying, the sigma we expect sigma transpose sigma to behave like gradient of f squared, okay? So it's natural to assume these things, okay? So here the Polya-Ložović condition, instead of asking that A is lower bounded, is A minus eta G max that needs to be lower bounded, but eta is as small as if we want. G max is going to be bounded. So it's a stronger condition than Chatterjee, but when eta converges to 0, we get exactly Chatterjee's condition. And this really comes from Ito's formula, right? So this is the term Ito's formula. And here there's a martingale term that you can also treat. And at the end, you can show, which is here in this lemma, right? We can show that this lim sup of this quantity is less or equal of minus theta on the event that we haven't exited the ball and we haven't attained the minimum in finite time. And this theta is exactly this object here that is strictly positive, so this converges to zero. So f converges to zero exponential. Okay, so this is really the key ingredient. Okay, and right, so this slide only explains this, what I was saying in words, that this is the classical Pauli-Lojasiewicz conditions, that Chatterjee asks something which is local, which is much weaker than most of the literature. And we ask something which is slightly stronger than Chatterjee because they have this term that comes from the noise. Okay. Right. Okay, so I skip this proof. And now I go to the application to deep neural networks. So remember that we had this function in this case where f is a fully nonlinear neural networks. Okay, so here comes the assumption that fw equals to 0 is equivalent of saying that y is a function of some w star x, right? So this in practice, of course, is not typically the case, but this was the first step to later consider the more general case where this is not necessarily true, but then the conversion will not be to a point, will be to a certain distribution, okay? We also assume that our data has compact support, okay? So this is natural. And then we need to assume something of this type to show this condition, which is that the minimum eigenvalue of the expectation of x transport is positive. This is also classical in this type of works. This is to show this local PL condition, right? So we have the set of global minimum, which is non-empty. And then, okay, before talking about the initial condition, I talk about the activating function. So which activating functions do we allow? Well, as you see here, this is a theory based on Ito. Ito demands that the function are C2. So the activation functions for us are C2. So ReLU needs to be smooth in order to be applicable to our theorem. Then we also have this condition to be able to show the PL conditions locally, which is that the derivative of V is strictly positive and V of 0 is 0. So these are the assumptions of the activated functions. And then we also need some assumptions on the initial condition. The initial condition is, so the process is initialized at a point W, so a parameter W for which the bias are 0, and the first layer is 0. And all the other layers, each components, these are matrices, are non-negative. Okay, this is also to initialize close to the set of minimum. Right, so under these conditions, if gamma is the minimum of the entries of the initial condition that are assumed to be non-negative, and m is the maximum, then for all delta, there exists n and eta 0 that depends only on all these quantities, such that if the entries of the last layer are bigger or equal to n and eta is small enough, then this probability is bigger or equal to 1 minus delta. So remember, this is the probability of the process not exiting the ball, and here we are taking the ball of radius gamma over 2. Okay, so let me give you the intuition of that. Right, this was already in Chatterjee's paper, this kind of initialization. So the intuition is the following. If you imagine that you have this toy model W1, W2. So just multiplication by, so this is our neural network, very simple. And we are assuming that this is equal to Y, right? So we are looking at the W1, W2 that satisfy this equality, okay? So what we get, if we assume that W2 and W1 are non-negative, what we get is this set of global minima, okay? So what we are saying here is that the initial value, W1 is 0, remember? So that the initial condition is here, actually. So this is W0, right? And what we are saying is that it is gamma, right? So if we go here to the right, so the initial condition satisfies that W1 is 0, so that we are starting in the y-axis, okay, and the others are non-negative, okay? So this is gamma. So gamma is the minimum of the entry, so this is exactly the entry divided by 2. And the idea is to take gamma divided by 2 as the radius, and to take this as the ball of radius gamma divided by 2, right? So here we have all this set of global minima inside the ball, okay? And where we are proving in that with probability small as you want, depending on gamma, this converges to one minimum here, W star. Okay, so this is the toy example that shows the kind of initializations that we are looking at. Okay, and again, well, conditional on this event, it converges almost surely with an exponential rate that depends on all the parameters. So this is the idea. Okay, so this is the set of activation functions that you can use. Remember that the condition C2 is really the most restrictive, even with an approximation of Ito's formula could allow to get some general results, but otherwise you just get smoother ReLU or any function which is C2 and is strictly positive. The derivative is strictly positive. Okay. And so here, so this is the most difficult quantity to prove, because remember that I told you that we were looking at F to be the population expectation and not the empirical expectation, right? To prove the PL condition, okay, Chatterjee does it with the empirical expectation, but for the populational expectation, it's not always true, okay? So under our assumptions, okay, I don't have time to look at the details, but let's say that for the empirical laws, getting the PL condition to be satisfied is related to these neural tangent kernel matrices, which are the derivatives, which is the Jacobian of the gradient of the neural network, okay? And typically it's the minimum eigenvalue of this neural network kernel matrix that tells you if the PL condition is going to be satisfied, okay? But in the case of population laws, we don't have this type of inequalities, right? But for our particular assumptions and our particular networks, okay, using the ideas of Chatterjee for empirical laws, we managed to use the law of large numbers and to conclude that the local condition was satisfied for the population laws. Okay, so this is a point that is also technical. And just to finish, I just finish with some open questions that I already mentioned during the talk, but just to summarize. So we think it will be important to show that P converges to 0, data converges to 0. And so far, it's not clear how to prove, because the proof, as you can see, really doesn't show that. But we believe it might be true, and because of the Markovianity of the process. And also, we have a set of initializations for which the process converges almost surely. This could be also generalized to show that any arbitrary initialization, if eta is a small enough, convergence.